This is section 1E, part 2. We're now going to look at limits of square root functions as x approaches plus or minus infinity. And the first question I'd like you to consider is whether or not it's true all the time that the square root of x squared is equal to x. At first glance, most people want to say, yeah, sure, that's true. We like to sort of think of the square root as somehow canceling out the square. But in fact, that symbol always means to take the positive square root. So if you start out with a negative x value, you're not going to get a negative x value out of this. In fact, the square root of x squared is actually the absolute value of x, right? If you think about this, if I started with x equal 5 and took the square root, I would indeed get 5 back again. But if I started with negative 5, that would turn into the square root of 25. And I wouldn't get negative 5 back, I'd get positive 5 back, right? So I always get the absolute value of the original x value. But let's take that a step further. What is the absolute value of x? Well, the absolute value of x is the same as x, as long as x is already positive, greater than or even equal to 0. But the absolute value of x is the opposite of the original, the opposite of x, if x is less than 0. I'm going to use this when I start evaluating limits for square root functions. So here we go. I've got the same function here, x over the square root of x squared plus 1, and I'd like to evaluate the limit once as x goes to positive infinity and once as x goes to negative infinity. So let's take a look. Maybe I won't write it out this time. I want to make sure I save myself enough space. But just mentally, you can see that the top is going to become infinitely large, and so is the bottom. So this is an infinity over infinity indeterminate form. I'm going to start by borrowing the same technique that we were using with rational functions, dividing by the highest power of x in the denominator. In this case, the highest power of x in the denominator would be that x squared, but it's under a radical. So I'm going to have to write that as the square root of x squared. Now, of course, I have to divide by a form of 1 so that I'm not changing the value of my expression. But since there's no square root on the top, I'm just going to write the simplified form of the square root of x squared up here. And in this case, I claim I can just write that as x. Why? Because my x's are approaching positive infinity. I'm definitely in the x greater than or equal to 0 case, right? So when x is positive, the square root of x squared really is just x. All right, well now I'm in pretty good shape. X divided by x would be 1. And then all of this stuff is under radicals. So x squared divided by x squared is 1, plus 1 divided by x squared, all under that square root sign. And as x goes to infinity, a finite number divided by something really large goes to 0. So I'm going to end up with 1 over the square root of 1, or just 1. The limit is 1. And on the right, we have a horizontal asymptote at y equal to 1. All right, let's redo that same limit. But this time I want x to approach negative infinity. I'll start out essentially the same way, saying that I'd like to divide by the highest power in the denominator, the highest power of x in the denominator, which is x squared under that radical. Again, I have to divide by a form of 1, but I can put anything I want up here as long as it means the same thing as the square root of x squared. This time, because my x's are negative, they're approaching negative infinity, or in this case. So the square root of x squared would actually be the opposite of x. These are the same thing. They mean the same thing for negative x values. It's just a form of 1. So dividing on top, this time I get negative 1. And on the bottom, x squared divided by x squared is 1, plus 1 divided by x squared. That fraction, 1 divided by a number that's getting very, very large, that fraction goes to 0, and I have negative 1 over the square root of 1 for a limit of negative 1. So, on the left, my horizontal asymptote is y equals negative 1. Just for fun, because of those two different asymptotes, let's take a quick look at the graph and just see how that plays out in the graph of this function. So let's bring Desmos up here. And let's see, our original function was y is equal to x divided by the square root of x squared plus 1. And you can see the graph over here. You can already start seeing those horizontal asymptotes. I'm just going to adjust my scale a little bit. I don't need my y values to be that big. Let's just go from negative 2 to 2. There we go. And you can clearly see that over here on the left side, the end behavior as we go towards negative infinity has that horizontal asymptote. The graph approaches negative 1. And over here on the right-hand side, as the graph goes to positive infinity, or as x goes to positive infinity rather, the graph is approaching that positive 1 as a horizontal asymptote. So we're seeing in the graph exactly what we predicted using our algebra. All right. So that's one other type of function, square root functions. We've looked at rational functions, we've looked at square root functions. Let's look next at limits of log and exponential functions as x goes to some infinite value, positive or negative infinity. In order to do these, what I'm going to actually rely on is the fact that we probably all have a pretty good mental picture of the graphs of e to the x or e to the minus x. I'm just going to start by drawing them. Y equals e to the x, just a typical exponential growth function, right? Looks like that. And y is equal to e to the minus x would be reflected across the y-axis because of the negative, or you can think of it as your exponential decay function. And that one's going to look like this. Based off of those graphs, let's fill in our limits. These first two are for the e to the x function. As x goes to infinity, y goes to infinity. As x goes to negative infinity, looks like y is approaching the horizontal asymptote at 0. These two refer to the e to the minus x. As x goes to infinity, looks like we're approaching the horizontal asymptote, y is 0. And as x goes to negative infinity, the graph's end behavior is going up to positive infinity. I'm not necessarily suggesting that you memorize those, but rather that if you have that mental picture, that you can easily determine those limits quickly in your head. course, if you forget, not like you don't have a graphing calculator, you can always graph them, but these are worth having mental pictures of, just to keep you going smoothly through problems. I would argue the same way for the natural log function. Good idea to kind of have a mental picture in your head. The graph of y equals ln x looks like that. And so we would say the limit as x goes to infinity is going to be infinity. Notice that this keeps going up slowly. It doesn't have a horizontal asymptote. It doesn't go up real fast, but it does keep increasing. So it slowly goes towards infinity. What about the limit as x goes to negative infinity? Notice that that does not exist. Negative infinity, the whole left-hand side, in fact, of the plane, is not in the domain of the natural log function. So this is something we can't do. We're not in the domain anymore. Although it's not a limit as x goes to infinity or negative infinity, there is one more limit I'm just going to mention here while we've got the graph showing, and that's this one. We can only approach 0 from the right because the left side's not in the domain. But if we do approach 0 from the right, notice our graph is going to negative infinity. So I'm just going to put that in as a little note. If x approaches 0 from the right, ln x goes to negative infinity. And that's that vertical asymptote right there. All right, so keeping these limits in mind, and again, we'll use any of these limits freely at this point, let's go ahead and evaluate some limits that contain log and exponential functions. All right, in this first one, we have the limit as x is going to infinity of 1 over 3 plus e to the minus x. And all I'm going to do is say, I know this one, right? That's that exponential decay function. It goes to 0 as x goes to infinity. It's one of the ones we just drew a picture of in the box above. So this would be 1 over 3 plus 0, or 1/3. On the right, we have a horizontal asymptote at y equals 1/3. I'm going to start abbreviating asymptotes as HA and VA, so I have to keep on writing that out. Long words. All right, what about the same function as x goes to negative infinity? What's going on with this now? Again, that's an exponential decay function, so on the left end, it's actually really big. This is infinitely large on the negative infinity end. So what I have is 1 over 3 plus infinity. A constant, 1, divided by something infinitely large, always approaches 0 in the limit. So on the left, we again have a horizontal asymptote, but at y equals 0. Again, let's just take a moment and graph that, just for fun. Excuse me. We would have 1 over 3 plus e to the minus x. There we go. Here we are on the left end, our horizontal asymptote at 0. Here we are on the right end. Notice my scale here. This is 1 up here, so the fact that this is probably about 1/3 makes sense. We're looking at that horizontal asymptote at 1/3. So exactly what we predicted in our two limits. All right, we'll do a few more log and exponential examples. This time we want x to go to positive infinity, and we've got our function e to the x plus e to the minus x over 2. Let's see, as x goes to infinity, e to the x is exponential growth, right? It's this one. So positive infinity. E to the minus x, that's exponential decay. That's 0 on the positive infinity end. Over 2. Infinity divided by 2 is still infinity. And that limit is positive infinity. So my end behavior on the right, the graph goes up. All right, what about this next one? We've got the limit as x goes to infinity of e to the minus 2x minus ln x. Now this time we do have that e to the negative 2x, so let's talk about that for a moment. When we did the graph of e to the minus x, I did it very generally, right? I didn't try to plot any very specific points there. Would you agree that any e to the negative exponent will be a exponential decay graph and is going to have that same shape? So it really doesn't matter if that's e to the minus x or e to the negative 2x or e to the negative 5x. They're all going to have that same shape. And they're all going to be infinitely large on the left side and 0 on the right side. So when I go to do this one, we're going to infinity, and I'm going to say it behaves just like this. It's going to go to 0. Minus. As x goes to infinity, what happened to ln x? Remember that one? Ln x goes off to infinity. So I have 0 subtract infinity, or negative infinity. And behavior here on the right, the graph's going to go down. I can't spell behavior today. Slow down a little bit. Right and down. All right, one more. Limit as x goes to infinity of e to the x plus 6 over 2e to the x. Look out for this one. E to the x is the exponential growth curve. So as x goes to infinity, that goes to infinity, but so does that one. So this is an infinity over infinity case, right? This is an indeterminate form. When I have an indeterminate form, I always have to do some algebra to get a form that I can handle. Indeterminate forms cannot be evaluated directly. What I'll do is I'll use just sort of a slight variation on that whole idea that we used with the rational functions, dividing by the highest power of x in the denominator. In this case, it's not a power of x. It's actually e to the x. But I'm going to go ahead and try dividing by it. It reminds me of that same idea, so I'm thinking maybe it's going to help. So let's see, I'll get the limit as x goes to infinity. E to the x divided by e to the x is 1, plus 6 over e to the x. And on the bottom, the e to the x's will cancel out. I'll just get a 2. All right, the 1 and the 2 are no problem. What about this fraction? Well, that's a constant divided by something infinitely large, right? So that's like 6 over infinity. That's going to go to 0. So I just end up with 1 plus 0 over 2, or 1/2. On the right-hand side, we get a horizontal asymptote at y equal 1/2. All right, so when you do these problems that do contain the logs and the exponential functions, keep these 3 graphs in mind. In fact, if you got a bunch of them to do, or if you're working on a test where you can't look up notes, just making yourself a really quick 10-second picture of those three graphs can really help you as you start evaluating these kinds of limits. All right, we'll pause there and we'll come back for one last video for this section to deal with trig functions.